So in this chapter, we are going to jump into studying about our biomolecules, and specifically we're going to talk and look at carbohydrates. So when we talk about carbohydrates, these are things like glucose and sucrose and fructose. And when we think about carbohydrates in particular, we probably think about sugars, which we've got a cupcake here with frosting. We've got cookies, pasta, fruits. All of these things contain carbohydrates. So let's kind of introduce biomolecules and biochemistry, and then we're going to jump into an introduction of carbohydrates. So with carbohydrates, we begin our study of biomolecules, and these are just substances that are closely associated with living organisms. So a biomolecule is just a general term referring to organic compounds essential to life. And we sort of have four big categories. So our four big categories are carbohydrates, lipids or fats, proteins, and then nucleic acids, and these are things like DNA and RNA. Now, when we talk about biochemistry, this is just the study of the compounds and processes that are associated with living organisms, right? Now, biomolecules are organic because they're compounds of carbon, but they're also that starting point for biochemistry. And so these chapters that we're going to go over on biomolecules represent an overlap of the two areas of chemistry, organic chemistry and biochemistry. Now, carbohydrates are compounds with tremendous biological and commercial importance. These are widely distributed in nature, and they include familiar substances like cellulose, table sugar, starch, all of those things we talked about on the previous slide. We find that carbohydrates have four important functions in living organisms. The first is to provide energy, and they do this through oxidation. Then, they also supply carbon for the synthesis of cell components. And then they serve as stored forms of chemical energy. And then they form a part of the structure of some cells and tissues. When we look at carbohydrates, the name carbohydrate comes from an early observation that heating these compounds produced water and a black residue of carbon, which was incorrectly interpreted to mean that they were hydrates of carbon. The most striking characteristics of carbohydrates are the large number of functional groups they have. And so if we look at ribose, for example, And we're just going to list these as common functional groups that we find. Ribose has a lot of alcohol functional groups, and so we can see the alcohol functional groups here, 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 and here. So we have alcohol functional groups. It also has a functional group of an aldehyde, which is shown there. And then while this is not shown, we can also have a ketone functional group. When we have an aldehyde functional group, right here, sometimes this is written as CHO. So you need to be able to recognize kind of both of those in how we see the functional groups being presented. So because they have so many functional groups, these are referred to as polyhydroxyaldehydes or ketones. So each carbohydrate is either going to have an aldehyde or a ketone, but they're all going to have lots of alcohol groups. So carbohydrates are described as polyhydroxyaldehydes or polyhydroxyketones. And I just want to remind you that poly means many here, so that prefix means many. Another kind of definition is sometimes carbohydrates are classified like this because under hydrolysis they yield these compounds, or they give these compounds. So, or substances that yield these compounds after hydrolysis. Now, carbohydrates can be classified based on their repeating units. And so if they have one individual unit, that's called a monosaccharide. And in a future screencast, we're going to look at the different types of monosaccharides. So a monosaccharide is just a simple carbohydrate, most commonly consisting of 3 to 6 carbon atoms. Then we can have disaccharides, which are shown here. They're made up of 2 of the monosaccharides. So disaccharides are just a carbohydrate formed by the combination of 2 monosaccharide units. And I forgot to list oligosaccharides here. So we're just going to write it in. Oligosaccharides consist of 3 to 10 repeating units. And then we can have polysaccharides, which consist of really long chains of linked monosaccharide units, so greater than 10, but it can go up into the thousands. So polysaccharides are long chains of one of the properties of carbohydrates is that they exhibit a specific type of stereochemistry. When we talk about stereochemistry, this is just the way that the atoms are arranged around a molecule. And so I want us to look at glyceraldehyde, which is shown right here. Glyceraldehyde can exist in two isomeric forms that are mirror images of each other. Now, mirror images are called enantiomers, and they have the same molecular and structural formulas, but there's a different spatial arrangement of their atoms, and I'm going to bring models into class so that you can see this. Now, no amount of rotating these two can convert them from one structure into the other. And so we can make the comparison here, right, that these are like right and left hands. If you take your hands right now and put them on top of each other, what you're going to see here is that your thumbs don't match, right? And your little finger doesn't overlap with your little finger if they're right on top of each other. And so this is because your hands are non-superimposable mirror images, and molecules can have this same thing. And when they do, the two molecules are called enantiomers. And so these are just stereoisomers that are mirror images. So we can identify these stereoisomers that are mirror images by counting the number of different groups that are attached to a carbon. If there are 4 different groups attached to a carbon, then that's going to be what we call a chiral center, and that molecule then itself is chiral. So chiral is just the term used for compounds or objects that cannot be superimposed on their mirror image. Okay? And then chiral compounds are going to be carbons with 4 different groups attached. So when we look at glyceraldehyde, what we can see here is that this carbon right here has 4 different groups attached. There's a hydrogen, there's a CHO, which is that aldehyde group, there's a hydroxy group, which is an OH, and there's a CH2OH. And these are the 4 different groups. So we would say that's a chiral carbon, and we represent that with an asterisk. So a lot of times we put an asterisk next to the chiral carbon. Now, if 2 or more groups are identical, then it is not chiral. Now, let's do an example. So let's say we've got these two compounds, and it says which of the following compounds contains a chiral carbon. What we would do is we would start and we would just systematically go through and look at each of the carbons on each molecule. So we come to this first carbon and we say, well, it's got 3 hydrogens attached, so it can't be chiral. We come to this carbon and we say, well, it's got 1 hydrogen attached here and an OH, but this CH3 and this CH3 are the same, so it can't be chiral. And then we have this carbon, which has 3 hydrogens, and so that's got too many groups that are the same. So this molecule contains no chiral compounds. Then we come over here and look at this molecule. We have a CH3 here, so that's not going to be chiral. This carbon has 3 hydrogens. That's not going to be chiral. This carbon has 2 hydrogens. That's not going to be chiral because those are the same groups on a carbon. So we come to this carbon here in the center, and what we find is this carbon is attached to a methyl group here. It's attached to a hydrogen. It's attached to a CH2, CH3 here, and then it's attached to an OH down here. And so those are 4 different groups. And so this would be, that carbon right there would be considered a chiral carbon. So this molecule has 1 chiral carbon, and it's represented with an asterisk. Now, maybe the burning question in your heart is, can you have more than 1 chiral carbon in a molecule? And the answer to that is yes. So, organic molecules, particularly carbohydrates, can have more than 1 chiral carbon. For example, I've got ethros here for you, and it has 2 chiral carbons shown right here. Now, for whatever reason, the ethros structure is cut off a little bit. That should be an oxygen here. So we'll just finish that out with the oxygen. So when a molecule contains more than 1 chiral carbon, the possibility exists for 2 arrangements of attached groups at each chiral carbon atom. So nearly all molecules having 2 chiral carbon atoms can exist as 2 pair of enantiomers for a total of 4 stereoisomers. So let's put some of this down in writing. So organic molecules can have more than 1 chiral carbon, okay? And when they do, the max number of stereoisomers is 2 to the nth, where n is the number of chiral carbon atoms. So, for example, ethros has 2 chiral centers. And so what we would do is we would go, okay, that's 2 to the 2nd power, where the 2 chiral centers go in for the n, and that would give us 4 stereoisomers. So we could have 4 possible stereoisomers for this carbohydrate. So I want to do another example. So glucose is present in the blood, and the normal range after eating is 135 to 140 milligrams per deciliter. Identify the chiral carbons in glucose, and then identify how many stereoisomers are possible for glucose. So when we look at glucose, the structure of glucose looks like this. And as we go through, I would suggest doing this systematically. So we look at this carbon here, and it has a double bond, so automatically it can't have 4 groups attached. So now we're going to go to this carbon here. And when we look at this carbon here, we can say, okay, hey, look, this is a group here. Then this is a group here. Then this is a group here. And then this whole thing right here is one group. And so we would say, okay, hey, look, that is in fact a chiral carbon. And then we would go to the next carbon. And we would say, all right, let's look at this carbon here. When we look at that carbon there, we would say, okay, this is one group that's attached to that carbon. This is a second group that's attached to that carbon. This is a third group that's attached to that carbon. And this is a fourth group that's attached to that carbon, and none of those are the same. So that's also a chiral center. Okay, so now we go to the next carbon and we say, okay, so this is one big group here. This is a group here. This is a group here. And then this is one large group down here. And so now we've got 4 different groups, and that's another chiral carbon. So let's go to the next carbon. So now we've got this whole group, we have this whole group, we have this whole group, and we've got this whole group here. And so those again are 4 different groups that are attached to this carbon. Now when we come down here, this carbon already has 2 hydrogens attached, so we would know it's not chiral. So when we look, we've got 4 chiral carbons, and we've identified them with asterisk by each one. Now, that means we need to figure out how many stereoisomers are possible. So we're going to go 2 to the nth here, and so it's going to be 2 to the 4th, which is 2 times 2 times 2 times 2. And so that would give us 16 possible or maximum stereoisomers. All right, so this concludes our introduction to carbohydrates. As always, if you have any questions, please feel free to stop by my office.